Okay, good morning. So, since we had that little technical hiccup in the lecture on Tuesday, we just have a tiny bit to finish. Keep it down a little bit. Hey. Thanks. Yeah, we have a tiny bit to get through just from the lecture still, just to catch up, and then we'll get on to the practice class. So we've been talking about vector spaces. We've looked at lots of examples, sequences. Well, let's go back to where we were. Examples of vector spaces. Fn, that's kind of the most concrete one. F is the field of the vector space, and then Fn is just these column vectors with the natural operations. Polynomials is an F vector space, and polynomials of degree less than or equal to n is also an F vector space. Matrices are very important. Vector space, just with the natural operations. Remember a vector space, it's only got two operations. It's got the addition of vectors and the scalar multiplication, just to remember what we're talking about. Sequences. Sequences is kind of like, if I drew those sequences as column vectors, this is really just like a f to the power of n, but now n is infinity. So this sequence is one is kind of like the fn, but now n is infinity, and instead of writing them as big long vectors like that, we're writing them like that. Anyway. Functions from x to a field f, that's a vector space. And an important one that we talked about was if we have two fields E and F with F a subfield of E, then E becomes a vector space over F. Okay. All right. That's where we got up to. The next thing I was going to talk about was this lemma. So this is, as I said last time, this is meant to be something that makes us happy rather than sad. Like it's saying that all the sort of things you would hope to hold, do hold. Let's prove one of them, I guess, so we'll wipe off. The rest of them will be a tutorial, but let's just do one. So e.g., let's prove the 0v equals 0, 1, 3. So to do that, we could look at, we're trying to prove that 0v equals the vector 0, no matter what v is. And all kinds of ways of going about doing these things, but you've got to somewhere use some properties of 0, I guess, of the number 0. And then so that's something about just 0. Well, not number, field, 0 in the field. And then I'll use distributivity in the vector space. And then it's already looking pretty good because I just want to, what you want to do is cancel away a 0v from both sides. What does it really mean to cancel something away? It means, well, one way of saying it might be to try to subtract it from both sides, but we don't really, well, we do subtract in a vector space, we do think about, but if we're going to be very axiomatic about it, we really add the additive inverse. So that's the same thing. So let's now, therefore, so let's, and how do we do that? We're sort of not really doing it to both sides, we're actually just looking at this expression here. That's the additive inverse. That's 0 by field axiom. Vector space axiom. That's the 0 in vector space. Well, it's actually the additive inverse. And now, the point is now I use the formula I just proved up above. Oops, I put the twiddle on the wrong one. That's using this. Okay, replacing the 0 by... I could have, you know, it depends how you want to set these out. You could also start, I could have started here, written this, and then done this little bit of working. Maybe that would have been smarter, but anyway, whatever. But now I have to do something still. If I'm really going to do it axiom by axiom, I have to actually use associativity. To group them together differently. So 0v plus 0v plus the additive inverse of 0v. I have done something there. I've changed the way I'm grouping the addition. And then let's continue on down here perhaps. Now using the additive inverse. Axiom in the vector space. This is 0v plus 0. And then again, and then using the 0 axiom. This is 0v. So at the end of the day, I didn't do it the most elegant way off the top of my head like that. It probably could have made it one big long chain of equalities rather than doing this little working up the top, but the little working was how I started thinking about it. Okay, the rest can all be exercises. And the point, while you're doing them, you're meant to be thinking carefully, just checking you're only using one axiom at each step. Or, I mean, there is some efficiency in proving some before the others, and then using those other ones to speed up the proofs of the other ones. That's fine. That's fine how to prove the lemma. So, for example, knowing that 0 is unique, if you then, another way of trying to do this question would have been to show that this thing, if I'd already shown this, I could show that this guy is a 0. That would be good, because if that is a 0, then it's the 0. Okay, so that would have been another strategy to show that 0 times v behaves like a 0 vector in the vector space, and hence is the 0 vector. Anyway, there's various ways of trying to go about proving these. Anyway, we should continue on, because I want to get on to the practice class. So we didn't get to subspaces last time, but it's fairly obvious what we're talking about here. So a subspace of a vector space is a subset, of course, which is a subspace, which is a vector space in its own right. And again, just like with fields, you don't get to play around with the operations. It's got to be a vector space with the same operations that the original vector space had. Okay, so the same rule for the vector addition and the same rule for the scalar multiplication. In particular, it's going to have to be a vector space over the same field. You're not changing the fields when you're going from a vector space to a subspace. It's a vector, I mean, because it has to have the same rules. Part of that rule is the scalar multiplication, and part of the definition of the scalar multiplication is the field that you're talking about. Okay, so you can't have a ZP vector space as a subspace of an R vector space. That just doesn't make sense. Some examples. Did I freeze it? Yep. So is Q a subspace of R? And here it's not really a well-defined question, because often when the field is, implicit or something, so when it's clear what the field is, we don't write it, we just say vector space. But really, in this one, I really have to worry about how am I considering R? Am I considering R as an R vector space, which it is, that's fine, it's a one-dimensional R vector space, in which case certainly Q is not a subspace, because it's not closed under scalar multiplication by real numbers. But if I'm considering R instead as a Q vector space, then yeah, sure, Q is a Q subspace of that Q vector space R, because it satisfies all the axioms. We're going to get to the subspace criteria in a second, but it should be clear enough Okay, so it's a bit ambiguous. So no if R is considered an R vector space, or for that matter, a Q adjoined root 2 vector space, which it is as well. Okay. But yes, if R is considered as a, I guess, Q vector space. Is that clear? Yeah, sure. Say that again. So if I want to consider Q as an R vector space, if I want to if R is an R vector space, and I want to try to consider this subset Q and think, is that a vector space, a subspace, it has to be closed under the scalar multiplication. But the scalar multiplication in this vector space as an R vector space is multiplication by real numbers. And multiplying Q by a real number, I leave Q. So it's not that I leave R, it's that I leave Q. So Q won't be a subspace, because a subspace has to be a vector space in its own right, so these operations have to restrict down to that subset. In particular, it has to stay closed under those operations. Okay. I mean, these are really, really different vector spaces, these ones. This is a one-dimensional vector space. We haven't talked about dimension, but you already sort of know what dimension means. And this one is an uncountable dimensional vector space. Like huge dimension, not even just infinite, it's like really big infinite dimensional vector space. So make sure you understand what the difference is in those. It's all about what the scalars are being considered as. That makes a huge difference. Is Fn a subspace of this guy? Well, yeah, yes. There's no ambiguity. I mean, both are it's not, in this case, there's not really any ambiguity here. They're both F vector spaces. This is a situation where it's, there's no other natural thing I could be taking here. Yes, and how do we check that really quickly? It's a bit like the subfield criteria. Remember, once you know something's a field and you've got a subset, you don't have to check all of the field axioms because most of them will just have to hold because they're already held for the big field. Same with the vector space. You've got a subset. As long as you know it's closed under the operations, essentially, and I'll clarify that in a second, as long as you know it's closed under the operations, all of the vector space axioms just have to fall into place because they were true in the bigger thing. Okay? So again, checking a subspace is actually very, very fast. And so in principle, I just checked all the vector space axioms in my head, let's say, but I didn't really do that. What I was really doing was applying this criteria here. So a subset of an F vector space is a subspace if and only if these three conditions happen. And the first one is kind of important. It had better be non-empty. And the way you normally check it's non-empty, or the easiest way to think about it, is normally just that the zero vector should be there. I mean, this subset X will be given by, in practice, will be given by some kind of rules or formulas or something like that, the set of things satisfying some formulas, and it's pretty clear whether the zero vector is in there, almost always. If the zero vector is not in there, you're already sunk anyway, because it can't be closed under this addition here. Well, it can't be closed under scalar multiplication, is what I meant to say. But anyway, it's not empty, that's important, and then it has to be closed under addition and closed under scalar multiplication. Now, you might ask, what about it? Is that necessarily going to be closed under additive inverses? So if X is in there, is minus X in there? Well, yeah, it is, because minus 1 is in the field, and minus 1 times X by vector space axioms that by the lemma that we proved from the vector space axioms, minus 1 times X is the additive inverse of X. So the additive inverse of X will be there. Okay. So that's part of what you have to do in the proof. You have to check all of it's not, you actually have to write out the vector space axioms and check that just these three conditions, and of course knowing that V itself was a vector space, will verify all of those axioms for our subset. All right, so just to streamline that, non-empty, closed under addition, closed under scalar multiplication. Couldn't be easier than that. And here's some quick examples, and then we'll get on to the practice class. Okay, so these are some more notate. We haven't seen these examples yet. These are ones we'll use throughout the course. C naught of R, the naught is some kind of level of continuity. It's a zero continuous, so to speak. The next one, C1, it's like super continuous. It's in fact differentiable. But anyway, that's what these notations mean. So C1 of R are continuous functions from R to R. C1, sorry, that was C naught. C1 is differentiable functions from R to R. There are higher, you can talk about C2, C3 and stuff, but we're not going to need to. They're both subspaces of all functions. Why? Because of the subspace criteria. So let's just check. Let's do C1, for example. It looks like I'm doing C1 here. So the zero function's there, so it's non-empty. Okay, because the zero function is certainly differentiable. 0x equals 0, that's the zero function. And if I've got two differentiable functions, then my favourite rules of my linearity of differentiation rules, these ones here, tell me that the sum f plus g and also lambda f are both differentiable as well, with those explicit rules for the derivatives. Okay. All right, so it's a subspace criteria. Check those three conditions. All good? Another example that's useful sometimes to discuss and illustrate things is finite sequences. So what this one means, it's all of the elements in our sequence vector space, but insisting that after some point for each sequence, there's some point where they're all zeros after some point. Or in other words, there's only finitely many non-zero terms in each sequence. So they're not all bounded by a fixed thing, but given a sequence, you can look at it and at some point it all becomes zeros. Given another sequence, it might become zeros later, but every sequence has that property in this subspace. Now this is a subspace. Let's just check it in our heads. Yes, it's got the zero sequence. That's in there because that's certainly got finitely many non-zero xi's. If I add two things with only finitely many non-zero terms, I get something with finitely many non-zero terms. Why? Because, well, the first sequence, it was 0 after the kth place. The other one was 0 after the elfth place, let's say. So in the sum, after the maximum of k and l, it'll all be 0. And similarly, scalar multiplication, it's clear that it's closed. So by the subspace criteria, yes, it's a subspace. All good? All right, so sorry we didn't get through that in the lecture. The next is an appendix about constructing finite fields, so that's for you to read in your own time. All right, so I'll just get us onto our worksheet. Sorry. There we are. Okay, so now we're on to the worksheet. So the way these worksheets work is there's normally a heap of questions, lots and lots, with a lot of repetition in some of them too. So you do as many as you feel like doing before you get bored. Just make sure you understand what it is. And there's more than we ever get through in the class. But the point is, we'll just discuss a few things with them, and it gives us some time to expand on some of the things from the lectures, basically. So maybe the first one I won't explicitly do. You know how to do the addition and multiplication tables in Z12. If you don't, then, well, we can discuss it indeed. But, I mean, here you put the 0 up to 11 down here. 0 up to 11 up here, and in the boxes you do x plus y in one of them and x times y in the other table, two different tables. And it does say use these tables to explain why it's not a field. So the reason it's not a field is that there's not multiplicative inverses, and you're going to see that in at least one of the rows. So in the rows of the multiplication table, what should happen? So I'm not going to actually write it down, I'm just going to say it. In the row of a multiplication table, there should always be a 1 if you're a field, because x times something has to equal 1, and that something would have been the inverse. And for example, taking 4 in Z12, when you start doing 4 times 0, 4 times 1, 4 times 2, 4 times 3, and write them all down, none of them are 1. Okay, and we know why. It's because 4 has a divisor with 12. Okay. That's one reason why this is not a field. Another reason why this is not a field, again from the multiplication table, would be because when I look at 4 times 3 in the multiplication table, that entry is going to be 0. But the only time I'm ever allowed to have a 0, not by a field axiom, but by a property of fields, remember that lambda times mu equals 0 in a field forces either lambda or mu to be 0. That nice rule that we really like, of course. So 4 times 3 equaling 0 is another reason why we're not a field. So in any row, you should only have one 0, and that should be when you multiplied the thing by 0. Except for, sorry, the first row is all zeros, of course, the 0th row. All right. So I think that's all I want to say about that one. This next one, though, I do want to discuss. So a lot of examples to do. Now, we want to try to compute these fractions. Normally I actually don't really write things as fractions like this in F11, but what it means is 10 times 4 inverse. So really all we have to do is work out 4 inverse. This is really something about finding inverses. So let's do that one, for example. And then we'll discuss a little bit more about that. So I'll add a page in here. Okay, so in question 2 there, e.g. in Z 10 over 4 in F11, which is the same as Z11, okay, they're completely synonymous notations for the same thing. 10 over 4 means 10 times 4 inverse, that's what it means. So we need to find 4 inverse. Now first, for a very small field, I don't know if F11 is very small or not, but it's pretty quick normally to do this by trial and error. 4 by 1, 4 by 2, 4 by 3. I already can stop there because that's 4, okay, that's not 1. That's 8, which is not 1 in Z11. This is 12, which equals 1 in F11. So 4 inverse equals 3. So 10 over 4 equals, well, 30. And 30 is 8. Okay. In Z11. Is that okay? So I just did it by trial and error. And there's only finitely many things you have to check. I mean, you keep going. The worst I'd have to do is get all the way up to 10, which would be pretty annoying, but I could do it. But you're probably aware there are other ways of doing it. One way was essentially the way we proved that inverses exist in class. That was to use Bezout's identity to write 4 and 11. Write 1 as a linear combination of 4 and 11 using Bezout's identity. You probably don't remember how to do that. It's in a tute. I must admit I don't really remember how to do it either. So I'll go through another way of finding the inverse that's also, that has there's a formula for the inverse. Okay, so a more direct way or something. It is a really beautiful fact that a to the p equals a for all a in fp, which is also zp, remember. Okay, so that's called Fermat's little theorem. And there's tons of ways of proving it. They're all, you know, none of them are super hard, but they're super clever normally. We see a really, really quick proof when we do the group theory course, part of the course. So I'll delay it till there. Okay, so let's leave it until then. But that, of course, gives a formula for the inverse. Because if a is not 0, then a to the p equals a, tells us that a to the p minus 1 equals 1. Yeah, I mean, writing it with this way instead of this way lets you also, you don't have to exclude 0. That's why people write it like that rather than like that. But anyway, now we've got the formula where you're excluding 0. And so that says, and what did we use here? Well, I mean, we're using not a field axiom where we cancelled away an a, but that's okay, because we proved at some point that if lambda times mu equals lambda, or no, we wrote it as a times b equals a times c, then you can cancel away the a's if a is non-zero in a field. That was one of our little lemmas about working with fields. All right, so that says that a times a to the p minus 2 equals 1, and so we have the inverse. Now that's great, that's a nice formula. The problem is, like, if p was quite large, if you're a large field, raising a to a large power is going to be a very large number, but that's okay. I mean, the computer will do it nice and quick for you. Yeah. It should be a p minus 2, sorry, yeah. But let's do an example. Let's find one of these sort of ones in, I don't know, I might get into trouble, but maybe do 8 inverse in F23 or something. In fact, I think I had another one in mind that I might do. Let's do 20 inverse in F23. So this is arguably entering the realm where you don't want to do trial and error. Okay, certainly getting big enough. But it's also perhaps not the case where so by our formula, this is 20 to the power of 21, and arguably that's not something we immediately want to do either. Yeah, that's got, I don't know, 30 digits or something, or whatever. It's big. But of course you can do it all piece by piece, trying to keep your numbers small as you go. So, I mean, first of all, 20, maybe arguably a better version of 20, I'll just write it like this, is minus 3. I mean, it's arguably better, it's a bit smaller, because it's, yeah, because we're working in F23. Okay. And that's now minus 3 to the 21. Just the minus comes out the front because it's an odd power of minus 1. Okay, that's a bit better. I still wouldn't really want to do that, but that now is 3 cubed to the power of 7. You just start sort of factorising the, breaking up the exponent a bit. And the reason I've done 3 cubed is because that's 27. So it's gone just a little bit past 23. And so I can reduce it down a little bit. Okay. Yeah. Sorry? It just disappeared. Yeah. There we go. Thank you. So that is minus, with the minus still there, of course. And then 27, but 27 is 4. And we're getting there now, maybe, but you just keep going. So this is now 4 to the 4 cubed, I guess, squared times 4 still. And then 4, what's 4 cubed? At a certain point, I'm not very good at arithmetic, so 64, and what's 64 in -5? Okay, good. That could be a lie. So 4 cubed was 64, and we're 46 would be -5. Everyone happy? Okay. So minus 5 squared by 4. And now -5 squared is 25, which is 2. So I get -8. And -8 is 15, I think. Okay, so we got there without having to, use our calculator. I don't know if your calculator can actually do, well, of course it can do that, but it might give you times e to the some power. It might, I don't know if it'll do the mod thing, but anyway. Everyone happy with that? Okay, so there's a little bit of an art to making it work, without going into horrible numbers. All right, that is quite fun. Anyway, so remember that formula when working with this if you want. We're going to prove it later on, but it's a handy, very handy and very beautiful fact. Let's go back to some of the other questions now. Okay, this one is just asking us, are these vector spaces? So it's not a subspace criteria thing yet. It's, let's check the time, sorry. It's just vector spaces. It's normally super quick to check. We're not checking all the axioms and stuff. Oh, these are I'd be looking at a subspace of R2. So I am basically using subspace criteria because I know that R2 is a vector space. Let's think about it. Is this set non-empty? Yeah, 0 vectors in there. Is it closed under addition? That's right, yes it is. If I have an xy and an x prime y prime, then they'll satisfy y plus y prime equals 3, x plus x prime. And finally, is it closed under scalar multiplication? Yeah, I mean, if I replace x by lambda x and y by lambda y, the equation's still fine. So yeah, this one's all good. The next one, no and why? Yeah, scalar multiplication. Oops, scalar mult. So no. Next one. Yeah, no, and various reasons, but what's one quick reason? Yeah, the 0 vector. That's not one of the things in the subspace criteria, but it has to have the 0 vector. That follows from the subspace criteria, or just being a vector space. This doesn't have the 0 vector, so you're already sunk. The next one. Yep, takes a bit more time to think about the function ones, but that's fine, yep. If I have two functions whose value at 1 is 0, then the sum of those functions also has value 0 at 1. And any scalar multiple also has value lambda times 0, which is 0. Okay. So yeah, that's fine. And the 0 function's in there as well, of course. Next one. No, in either, because it doesn't contain 0 function. Also, it wouldn't be closed under scalar multiplication. Wouldn't be closed under addition. I mean, this one's just terrible for everything. Yeah, these ones we've already talked about. This next one. Perfectly fine. Yep, this one, if you have, sort of an x1 up to xn and a y1 up to yn, both satisfying this, then their sum will also satisfy 0 plus 0, which is 0. Any scalar multiple, lambda times all that junk, is 0. So it's fine. And this is, in fact, well, let's maybe look at this one here. This is kind of a really typical way of describing subspaces of Rn. In fact, everything in Rn can be written, every subspace can be written like this, as a solution of a system of linear equations, homogeneous linear equations with zeros over on, that means zeros on the right-hand side. So any subspace of Rn is going to be writable. We'll sort of discuss that as we move on, but this is kind of the typical situation, in fact, for Rn, or Fn in general. Whereas this guy is no good because of the 1 there. It doesn't have the 0 vector. So you really see the 0 being on the right-hand side was important. And it's sort of like this one, the 0 here too. Like it's sort of related somehow. So yeah, that one's fine. That one's not. That one's fine. Maybe you think through the rest. Okay, I'll just go through a handful of them like that. The next question is really asking about, it's sort of the same question actually, so it's more examples of the same stuff. Now we're sort of more explicitly talking about subspace criteria, even though in reality that's kind of what we were doing there. Because everything was already a subspace of some ambient thing that we already knew was a vector space. Or it was a subset of something that we knew was a vector space. Anyway, let's look at these ones. This one here, so we're asked, is it closed under scalar multiplication? And the answer to that is no, certainly not, because the vector 0, 1, 0 sits in here, but minus that vector doesn't sit in here. I mean, so minus 1 times that vector. So it's not closed. When your scalar is a negative number, you're in trouble. So no, it's not closed. Yeah, okay, it is closed under addition, but it's still not a subspace, of course. This next one with squares, that looks suspicious already for squares. Like subspaces and vector spaces in general, this is a linear kind of linear mathematics, linear world. You're not expecting to see squares and stuff here. This doesn't look like a subspace. But why isn't it a subspace? Is it closed under scalar multiplication? Yeah, it is. Like if you multiply this by lambda, that means everything gets multiplied by lambda, and you'll just get a lambda squared common to everything. But this is already 0, so that's 0. So it is. It's got that one, but it's certainly not closed under addition. Okay. There's two numbers which sum to. Two things whose squares sum to 0, then you look at sums of two such things and expect the square to sum to 0. That's not the case. Okay. Yeah. Let's say you've got x, y, and then u and v, both with x squared plus y squared is 0, u squared plus v squared equals 0, and then you're trying to look at x plus u squared, y plus v squared, and that's, of course, not going to be 0 in general. Okay. This one, we sort of already discussed this. This is certainly linear land. That's good. The next one, no, it's not closed under scalar multiplication because I multiply by 17 and it'll equal 4 times 17. It's not closed under addition and not closed, not a subspace. Yeah.
Can we just check? So we said that R2, so the right?
Yeah.
But in order for x squared plus y squared to equal 0, the only condition.
Oh, okay, good. I was working over thinking of complex numbers or something. You're 100% right. This, if insists, this is, you're 100% right. I tricked myself with this question. This actually just means that it's this. Sorry. Yeah, it's a vector space. Over the complex numbers, no. You know, if it was a C vector space. Sorry. Yeah. In the reals, we certainly have this special property that x squared plus y squared equals 0 forces x and y to be 0. If we're working over F3, F5, if we're working over F5, then, yeah, good. So let's look at this again. If this was an F5 vector space instead, it won't be a subspace. Because there you can have 1 squared plus 2 squared is 0. So that's going to be in there, and then you take two such things, and that's not the vector 2, 3, 2, 8, 2, which is 2, 3 is no longer in there. So, anyway. Yeah, good. Okay, yep, sorry. The real numbers. This one here, it's not closed under scalar multiplication because I can multiply by 0 and I'm in trouble. It wouldn't satisfy that anymore. And it won't be closed under addition. Or that. Is that all okay? And so on and so forth. Maybe we'll finish off the last two. Because I realise now question 5 is about spanning sets, which, sorry, I should have moved that to next week's one. But maybe we can discuss it anyway in a second. Let's quickly look at these, though. This one here, so it's a subspace of all functions from R to R. Is it a subspace? So it looks closed under multiplication. That's fine. Is it closed under addition? No. Yeah, that's right. I mean, unless they... No, it won't be closed under addition. Just, you could... Yeah, no. Either 1 or 0 is... Exactly. Either 1 or 0 is 0. Either f of 1 or f of minus 1 is 0. But when you add two such things, that won't be the case. Because you could add one that was 0 here and one that was 0 on the other one, and then the sum won't be. So I meant to put a tick here. It is closed under multiplication, but not here. Polynomials. All the polynomials such as f of 1 is in Q. That's closed under addition, but that's not closed under scalar multiplication, because scalars are the reals, because this is a real vector space, or whichever one we're doing, and multiplying a rational by a real will kill that property. Polynomials of exactly degree n, no, it doesn't contain the 0 vector, but it's not closed by multiplying by 0. It's not closed under adding, because I add the negative of something and it'll escape. And so it's certainly not this. Complex, all the z, this is just plus or minus 1. To not get confused like I did earlier. But yeah, of course that's not closed as a C vector space. It doesn't really matter how C is being regarded here. If C is being regarded, the minimum, the smallest field I could put in there is Q. Okay. So, and why is Q the smallest? Because I have to have 1 in there, and then I've got 1 plus 1, I've got all the integers then, but then I have to make it a field, and Q is the smallest field that contains Z. So it has to, at least at the sort of most favourable situation would be I consider this a Q vector space, but that's already not closed under scalar multiplication by Q. But it's also not closed under addition, certainly not a subspace. Now, Cn as an R vector space. So remember what that means. So Cn are all vectors of length n with complex entries, but the multiplication is restricted just to real numbers. The scalars are real numbers now that I'm multiplying by. And Rn is now the subset of those complex vectors where all of the entries were actually real numbers. Okay, and that's certainly a subspace because I add two such things. It's going to be real entries again. I multiply it by a scalar, being a real number. Then I get a real numbers in all the entries again. So it's all good. But of course, if it's a C vector space, this one is still fine, but now it's not closed under multiplication because my scalars, I've got a real vector, I multiply by a scalar being a complex number, I leave the reals. Okay. Okay. Maybe let's leave spanning sets for another day, because we'll talk about that in lectures next week. So a tiny bit early. Are there any questions? Yeah. Keep it down for a second. Sorry, say it again. Yeah. So that we... Oh, no. In fx, yeah, so I think the question is that in this vector space, or also ring, fx is the degree finite? Yes, in this, what it means to be a polynomial here, it means that an element of this, it means that you're something of the form, let's call it p of x, you're of the form a0 plus a1x plus da-da-da plus an x to the n for some n bigger than or equal to 0 and with all of the ai's in f. But so every element of this polynomial ring is a polynomial, not a series. There is a ring where you just look at the so-called formal power series in x, and it's got an imaginative notation of just adding two lots of brackets there. This now consists of everything where I just let this go dot, dot, dot forevermore. Okay. Fx has, each individual polynomial has a bounded degree or a finite degree, but overall, of course, the polynomials in this set, their degrees can get bigger and bigger, of course. Yeah. But each individual polynomial has a degree. Any other questions? Yeah.
So where's this like fx, which is that? And I remember we looked at fx with like sub n.
Yep. And then fx with sub n. So this one we didn't really talk about, so I'll just cross it off. But fx sub n are all of the polynomials in f of x which have degree less than or equal to n. Less than or equal to, like either. Inequality here, not equality. Yeah. Okay. And that guy there is an F vector space, fine. But this one's not a ring. This one is a ring. I multiply two polynomials, I get a polynomial. This one, if I try to multiply polynomials, that's not part of the vector space operation. That's a ring operation. Of course, I'll start increasing the degree past this bound. Say again?
What field is x like
oh yeah, so x here is a formal indeterminate. You shouldn't be thinking of x as actually being a number or it's a symbol. In a way it doesn't exist. You can really imagine this polynomial as just its sequence of coefficients, but then the multiplication rule is very kinky. I mean, it'd be hard to remember a sequence times a sequence is however polynomials multiply. But we know how polynomials multiply. Okay. So x is just a figment of the notation, in honesty, but it's a very convenient part of the notation to make multiplication easy. Okay. It doesn't live anywhere in a certain way. Okay. All right, good. See you Monday. Yeah. real numbers considered in two different ways. So the real numbers are the real vector space, one-dimensional. By just one, another one, another one. But the real numbers considered as a vector. Say it's dimensional, I need to take any. To have, if I have any finite set of real numbers, and I take all of the Q linear functions, so I don't get it exactly. The real numbers considered with two different fields.
You know what this means?
That's just a C. It's just a curly C. This is functions from R to R that are continuous. And this one, this notation. The 0 and 1 are just notation. Well, I mean, this is the meaning. Yeah, this is the meaning.
So it can be any number you want.
Oh no, you can't. No, but with this notation C with the 0 is by definition continuous functions. This notation C with a 1 at the bottom is differentiable functions. You could define C with a 2 to be twice differentiable functions.
So like here, how come this isn't closed under multiplication?
Okay, because Rn, if the scalars are now complex numbers. So when I multiply a real vector by a complex number, I no longer get a real vector. So it's not closed under scalar multiplication.
I thought we're multiplying two vectors that satisfy this condition.
No, so because in a vector space we don't multiply vectors. In a vector space we multiply a vector by a scalar. That's the operation that exists in a vector space.
Okay.
So and the scalars are C, the vectors were real vectors, and multiplying a real vector by I or something will make it a non-real vector. Okay. Good. We'll talk outside. Okay. Yeah. That's okay.
What's the silence mean?
Yeah.